Hello, my name is Caleb Hill. I'm an alumnus of the University of Colorado, Colorado Springs, where I recently earned my master's degree in electrical engineering. Today, I'll be presenting a paper that I worked on during my time at the university with the assistance of my graduate advisor, Dr. Lee, concerning the classification of radio signal modulations using a convolutional neural network. In this presentation, I'll begin with a brief introduction of the topic. I'll cover some motivations and explain why one might opt for a neural network approach. I'll discuss the data synthesis and pre-processing used to train, validate, and evaluate the model. I'll talk over the model architecture and training, as well as some training observations as related to the data synthesis. And finally, I'll discuss the results in the form of model evaluation and observations on performance, followed by conclusions. Signal classification has tremendous value across a range of disciplines, some of which I'll discuss in a moment. Traditional methods of signal classification required expert knowledge and features extraction and are both expertise demanding and time intensive. However, convolutional neural networks combined with software-defined radio provide new means to develop classification schemes that offer reduced complexity in achieving similar results. Here, we propose the adoption of a convolutional neural network to digest complex valued signal data with minimal pre-processing to predict the modulation type. This method is shown to accurately classify many signal modulations, and the primary error is in predicting the order rather than the class of the modulation. The motivations for a signal classification system are numerous. Accurate classification of radio signals can enable more efficient use of the limited authorized spectrum, which is crucial for communications engineers. From a security perspective, rapid classification of nefarious transmissions can help detect invisible threats before a security incident occurs. For military applications, accurate detection and labeling of signals can alert to the presence of enemy forces or remote-operated weapon systems. There are likewise numerous reasons to adopt a neural network-based approach for these tasks. For instance, the proposed method avoids the added calculation complexity for statistical or moment features, or the considerations for properly designing phase-locked loops. Instead, complex valued temporal radio signals can be input directly with minimal pre-processing to the convolutional neural network. The proposed signal classification scheme was implemented in 3 parts. First, the requisite data to train and test a network was synthesized. Without the presence of data, any network designs could not be evaluated. Second, the network and supporting software were designed to digest the synthesized data for training and testing. Finally, the network was experimentally trained with sets of synthesized data varying in size from very small data sets of minimally varying signal-to-noise ratios to substantially larger, more varied SNR collections. Datasets for the model training and evaluation were generated using MATLAB scripts and the DSP toolbox. Data was synthesized in frames consisting of 1,024 complex valued samples. Digital modulation was created from random bit sequences per frame instance at 8 samples per symbol. Additive white Gaussian noise was simulated at varying SNR ranges to simulate more realistic conditions. All frames were created at a sample rate of 200,000 samples per second with randomly varying center frequencies. When we created the frames, a 1024-point discrete Fourier transform is taken of the complex valued samples. Each modulation frame was saved as a uniquely labeled file containing the complex valued temporal samples, the DFT samples, and a label of the signal-to-noise ratio and the modulation type for the frame. Pure white noise frames were also generated for training the network to recognize no signal condition. This was an addition from previously studied models and based on the assumption that a real-world implementation would need the ability to classify the lack of a signal accordingly. This slide visually demonstrates the in-phase and quadrature data for the synthesized signal frames. As mentioned before, each frame is 1024 data points long, as indicated by the x-axis of the figures. This is a visualization of the 1024-point discrete Fourier transform data for each modulation type. Note that the transform data is not shifted to center at 0 Hz, so the spectral wrapping occurs at the far left and right of each figure. This figure demonstrates the continuous finite phase difference of the IQ data. The angle difference of the IQ data is not unwrapped here, so the maximum detectable difference is plus or minus pi. This data was not produced at frame generation time and was instead extracted from the complex IQ samples immediately preceding input to the convolutional neural network. The proposed network architecture and design are inspired by O'Shea and Clancy's work using convolutional neural networks for signal classification. In their experiments, a visual geometry group convolutional neural network was adopted and modified to accept a 2 by 1024 point input, representing the real and imaginary IQ values as 2-column input data frames. In this experiment, a similar VGG model is further modified to accept a 5 by 1024 point input, consisting of the IQ samples as columns 1 and 2, the discrete Fourier transform of the synthesized data as columns 3 and 4, and continuous finite phase difference as column 5. The model is visualized in the figure here on the left and described in the table. In this model, fully connected layers are SALU activated with a final softmax output layer. The loss function for model execution is categorical cross entropy, and the model employs the atom optimization algorithm. Training the model was conducted in several test stages before arriving at the final training volume and signal-to-noise ratio levels. The training set was ultimately comprised of 10,000 frames per modulation type per SNR value and an additional 10,000 frames of pure white noise. Frames were generated at SNR values of 10, 20, and 30 dB for training. The total training data set is 340,000 frames. Training was performed in 10 epochs. Validation data was also generated in an identical but separate process consisting of 2,000 frames per modulation type and SNR level. Testing data was also generated like the validation data, excluding white noise frames, and totaled 1,000 frames per modulation type at SNR values ranging from -40 to +40 dB, with additional points taken near 0 dB, to highlight model performance as the modulated signal becomes the dominant energy source in each frame. Testing results are presented in a moment. There were some interesting observations from the early training processes. If the network was only trained with 10 dB SNR frames, model accuracy never exceeded 72%, even for high SNR inputs. Training the model exclusively with frames synthesized at 30 dB SNR excels at high SNR classification accuracy, but performs poorly, just decreasing to 20 dB. Providing low SNR data in addition to high SNR frames improves the accuracy of weaker signals. This was the motivation to use 10, 20, and 30 dB SNR frames as the final training input. Model convergence is minimally improved by the addition of low SNR frames if there are not sufficient high SNR frames in the dataset. Providing training data with very low or negative SNR values yielded negligible positive results and was instead more often found to harm network convergence. The classification accuracy versus signal-to-noise ratio for each modulation type is shown here, with Gaussian frequency shift keying showing the most recognizable characteristics and highest classification accuracy. Though by 20 dB SNR, most modulation types are classified accurately 90% or better. Higher order quadrature modulations are noticeably difficult to classify. This is not especially surprising since these modulation types also require a higher SNR to operate effectively. Quadrature amplitude modulation types are clear examples of this. However, while the classification accuracy of some modulations is noticeably lower from the figure here, this chart does not show the whole picture. This confusion matrix shows the classification prediction results for a separate testing dataset comprised of signals with signal-to-noise ratios of 10, 20, and 30 dB. Note here that 16 QAM and 64 QAM modulation types are often correctly classified as quadrature amplitude modulation, but their order is confused. Similarly, QPSK and 8PSK are often misclassified to the wrong order while still correctly identified as phase shift keying modulation types. Note, the same observation can be made of single sideband and double sideband modulations. Interestingly, sideband modulations also represent the most common erroneous classification as noise. This could be due to the lack of a constant carrier, which undoubtedly is a strong distinguishing characteristic from pure noise that is present in other modulation types. In conclusion, this demonstrates accurate signal classification can be achieved with minimal input processing, and therefore avoids the complexity and considerable time in devising the appropriate expert features extraction of traditional classification schemes. The classification accuracy exceeds 90 to 95% for many modulation types at signal-to-noise levels required for reliable data communications. Moreover, a substantial portion of the misclassifications are in the order rather than the type of the modulation. Further improving classification accuracy, particularly in the case of PSK and QAM-type modulations, might be achieved by further refining the training data set and the order in which the training data is fed to the network. Likewise, further examining the optimal mix of high and low SNR training data will likely improve results further. These will be the focus areas of future research. In closing, I'd like to express my thanks to my graduate advisor, Dr. Lee, who first introduced me to the topic of deep learning and made this research possible, to the Department of Electrical and Computer Engineering at UCCS, and to Paul Gavrikov for his work developing the Visual Keras tool, which has become an invaluable tool for me in expressing how a model might look from conceptual inception to implementation. Thank you for your time.